Yan, no, sorry, Wei. So we are very happy to have Yan Zetian from UCSB. The title is Recent Progress on Fourth Order Willmore Energy. Okay, you can get started, Zetian.
Okay, so thanks for the introduction and invitation, and I'm very happy to share my work joined with Nawu and Jejo in our workshop. So the title is Recent Progress on Fourth Order Wormhole Energy. Since this topic is developed in recent 5 or 6 years, so I will spend some time to introduce the background on this high order, okay, wormhole energy, and introduce several, recent progress joined with my collaborators and further problems we are working on. Okay, so so first of all, let's briefly review classical wormhole energy. Classical wormhole energy exactly a functional defined on an immersed closed surface. So it can be regarded as the L2 norm of mean curvature. And here, for convenience, I use the averaged mean curvature, okay? So wormhole energy can be regarded as a measurement of the, curved surface, right? So why wormhole energy is so important in geometric analysis? Because it's invariant, okay, under conformal transformations on the Euclidean space. Here, let me emphasize conformal transformations in Euclidean space consist of translation, dilations, rotations. Okay, so of course you want to say inversions, right? But the inversion will change the orientation. So when we when we apply inversions, we need to compose it with translations. So usually, I should say it's a spatial conformal transformations. So it means you can apply the inversion and do the translation and apply another inversion. Okay, so the orientation will be preserved. Of course, if you would like to check, okay, the conformal invariance of the wormhole functional, here is a convenient way by Gauss equation. Okay, we can decompose wormhole energy into two parts. So the first part, I call it pointwise conformal invariance. Another part provided by Gauss curvature, and of course, by Gauss bond formula, you will see that the total Gauss curvature exactly right the Euler characteristic. And for the first part, let me say more about it. Because under the conformal transformation, we will see that since right now the dimension is 2, right? So the volume is given by the following transformation law. Okay, moreover, so this part is exactly the trace-free second fundamental form. So it will be transformed by the following formula. And you will see that the conformal factor will be cancelled. So this part is exactly a pointwise conformal invariant. Okay. So if you would like to generalize wormhole energy to higher dimensions and manifolds, so the question is how to find global conformal invariance on an embedded closed hypersurface. And here for convenience, we just consider hypersurface case, okay? And the dimension is 4. So probably you will have a question, why the dimension must be even? So to the best of my knowledge, there are 2 reasons. The first reason is if the dimension is even, we have Gauss-bonded chain formula, right? So we have some topological invariance. And the next reason is the following. Because under the dilation, okay, so the volume will be changed like this. And here is the dimension. And here is the original volume. And we will see that if the dimension is odd. So if n is odd, and we will discuss the sign of the geometrical quantity in the integrand. So for this reason, we usually consider, global conformal invariants defined on submanifolds with even dimensions. So we can consider sigma 4, sigma 6 like this. Okay, and the answer of this question, I would like to split it into two parts. First, I call it several trivial global conformal invariants. So as I said before, right now we have polar characteristic, right? So it's exactly a topological invariant. Of course, it's invariant under conformal transformations. Next, we have pointwise conformal invariants, the analog of A square, okay? And here, if sigma 4 is exactly a hypersurface, and this space is spanned by the following two integrals. And you can, if you are very interested in it, you can check it by yourself. In general codimension case, right now we can decompose the following tensor. So here, let me emphasize, since we can regard the second bound non-final form as a two tensor taking value in normal bound, right? So if you consider their product, so you will find that you have two index, alpha prime and beta prime. And you can break it into symmetrical part and anti-symmetrical part and do the suitable contraction as we did, okay, previously. So you will have four, so let me emphasize, you will have four invariants in higher codimension case. So in this page, you will find that all of these global conformal invariants, in some sense, they are trivial. And there are two more non-trivial, okay, conformal invariants. First, this guy, I call it Rubin-Grimes energy. So it's an integral of the leading term in this functional, exactly the gradient L2 norm of curvature. And here, this is the normal connection. And of course, we need some lower order terms because we need their linear combination is invariant under conformal transformations. And later, I will briefly introduce the discovery of this functional. Of course, in higher dimensional case, there is one more global conformal invariant, and I call it capital I. So this invariant is discovered by my PhD advisor, Jeffrey Case, and his collaborator, Rubin-Grimes, Cosmo, and another two collaborators. So this global conformal invariant consists of bus tensor, cotangent tensor, and their derivatives. And you will check it, sorry, if you are very interested, you can check it by yourself. In the hypersurface case, okay, this invariant, it vanishes. Okay, so in this talk, we will mainly focus on this functional because it's well defined, okay, when embedded the dimension bigger than or equal to 5. So the discovery of this functional, so firstly, it was discovered by a physicist, Govan, okay. So Govan's idea is the following. He would like to find a functional with a leading term, gradient L2 norm of mean curvature, and then he plus several potential low order terms. For example, we can add several low order terms. And the key point is we expect, okay, this functional is invariant under conformal transformation, the variation under conformal transformation, such that you can determine the coefficients. Okay, and he discovered this functional. Okay, in hypersurface case, and in general codimension, Rubin Graham and his student Richard and Zhang Yongbing, okay, a professor in China, they reformulate Gover's functional and link it with something called renormalized area. So link this energy, let me see, link high order Willmore energy to the renormalized area. And the renormalized area is a very known, okay, conformal invariant in this field. So they will check the conformal invariance for free. If the embedded space is curved, okay, is curved. So my advisor, Jeffrey Case, and his collaborators not only construct high order Willmore energy, they construct extrinsic GGMS operators. So in other words, they construct a family of, conformal covariant operators and show that in some critical dimension, the extrinsic Q curvature can provide the Willmore energy. Okay, so it sounds like they did more work in this field. And later I will show that their construction is very useful in the study of high order Willmore energy. Okay, so from previous discussion, we find that in dimension 4, right, we have a lot of choice for the global conformal invariants. So this is a different phenomenon as dimension 2, because in dimension 2, okay, so the only two global conformal invariants is provided by this part and this part. Okay, so you can see that you can do the linear combination, but the canonical one exactly the classical Willmore energy. So for this reason, a lot of physicists and conformal geometers, they are looking for the canonical fourth order Willmore energy. Because if you choose different, coefficients, right, probably this functional will have some, specific meaning in physics. However, from my point of view, I think in different problem, we may choose different fourth order Willmore energy. For example, if we consider Willmore problem says that for fixed gene, okay, P non-negative, and embedded dimension bigger than or equal to 3. We consider all emergence, okay, from closed orientable surfaces with a fixed gene. And we consider the infima in this class. So the question is, can we find a smooth immersion realizing, okay, this infima? The solution of this problem can be divided into several cases. For example, when P is 0, topologically it's a sphere. So we can find a uniform lower bound for this Willmore energy is 4 pi. And the equality hold if and only if it's a round sphere. I think the quickest way to give the proof in this case is the following. We need the conformal area introduced by Peter Lee and Yao. So this is that we may consider the immersion into S3, because if you consider the stereographic projection, okay, you can equivalently you can consider immersions of this surface in S3. Right now, the Willmore energy is no longer H square. You should plus the constant one. The reason is the following, because R3, right, exactly the constant, okay, space form with constant 0. But S3, the constant is equal to 1. And you can find that the trivial lower bound is exactly the volume. And you can consider the infima along the okay, the all of the conformal transformations, and you will see that the lower bound exactly 4 pi. Okay, and then later I will introduce the analog of this conformal area. Okay, and when P is equal to 1, topologically it's a torus. And Leo-Simon used geometric measure theory to prove the existence of a smooth minimizing Willmore torus. Okay, and when P bigger than or equal to 2, so Leo-Simon proposed a criteria. So this is a criteria. Here, E, okay, this guy can be regarded as a function of the genes, okay, and this criteria can be regarded as a concave condition or a concave property. Concave property of this function. So the geometric interpretation is the following. Let me see it in the following way. For example, if we have a minimizing sequence with a fixed gene equal to P, however, in this minimizing process, we were, lost several topology. For example, this part, let me use different color. So the left part, I denote sigma 1, and the genes is P1, and the right part is sigma 2, is P2. And if we were lost, okay, the right part, and you will see that in the middle, okay, we will use a very small neck to connect this part, such that the Willmore energy of this surface or of this connect sum is approximately sigma 1 plus sigma 2 and minus 4 pi. The reason is the following, because we need to cut, okay, a small disk. And when we cut a small disk, we will lose energy 4 pi, and 4 pi exactly the energy of a sphere. However, when we do the connect sum, okay, we will, add another disk, okay. So this guy has a triple lower bound exactly beta P1 plus beta P2 and minus 4 pi. So if this guy is a minimizing sequence, this energy will converge to beta P. And you can find out exactly a contradiction, right? So in other words, Leo-Simon's criteria can be regarded as, a condition to avoid the splitting phenomenon, okay, in the minimizing process. And if you would like to, quantize, okay, this estimate here, you will need Coulter's, okay, Banner and Coulter's estimate, and they can construct, okay, to test surfaces and use the biharmonic function to do the interpolation in the middle neck region, and you will obtain this estimate. Okay, and the key point in this process is the following theorem. So as I said before, in this process, right, you need to cut a disk and do the connect sum. And in this process, you need to estimate the change of the energy. So this theorem says that we can use the inversions, okay, to make it regressive. And if you have the point 0 in this surface, and if you would like to use the inversion to block this point, you will lose the energy 4 pi and times the number of the pre-image, because each end will become, a flat plane, okay, asymptotic. Okay, so based on the reservation of Willmore and based on the solution of the Willmore problem, we are going to, of course, we would like to formulate, right, a higher order Willmore problem. And in this process, there are two problems. The first problem is which functional is suitable. So, of course, we would like to use Rubin-Grimes energy. The reason is the following. Because in the construction of Rubin-Grimes energy, here, you will see that here is h squared, here is h squared, here is h4. So when we calculate the Euler-Lagrange equation, you will find that minimal surface will become the critical point of this function. So it sounds like for this functional, okay, it has many critical points. Unfortunately, Martino, okay, construct an example, and he showed that for any closed hypersurface, and we can pull up this hypersurface. So it says that we can do the dilation such that we can find a family of hypersurfaces with fixed topology, but they will converge to S2 times R2 in Gromov-Hausdorff sense, and such that the energy will go to negative infinity. So in other words, Rubin-Grimes energy, okay, we cannot find a uniform, lower bound for it. And for this reason, I consider the generalized, okay, fourth order Willmore energy. We can add several lower order terms, such that if the parameter bigger than this number, we will have the uniform lower bound. Here, as you can guess, 4 times pi square exactly the energy of the sphere. Okay. So totally similar to Peter Lee and Yao's idea. I think the quickest way to do it is introduce something I called fourth order conformal area. So we may think in the following way. Right now, we can consider the stereographic projection and the immersions into S5. Okay. Again, in S5, the formula of fourth order Willmore energy will be changed. To be more specific, Rubin-Grimes energy in S5 is given by the following formula, because S5 is a constant, space form with constant 1, right? And you can find that we have two lower order terms. Okay, and right now, if you add this part, because this part is a pointwise conformal invariant, so even though we consider the stereographic projection, okay, it will not change, such that we can find a uniform lower bound, and I call it a fourth order conformal area. And here, I should say, we can take the infima among the conformal transformation group. And of course, you can drop h square such that you can find the volume. And this guy, you can, repeat Peter Lee and Yao's calculation and find that the lower bound is exactly 8 times pi square. Okay, so
here is 4 dimension, the same as 2 dimension. Peter Lee and Yao, that's 2 dimension. I'm correct or not?
Yes, they did the proof in 2 dimension, but you can, but you can repeat their argument, because if my memory is right, they can choose some test function, and this test function have some, balanced condition, okay? And you can estimate the lower bound of this volume. Exactly the same.
Yeah, okay. I think they use some kind of eigenvalue, I'm correct or not?
Yeah, they use an eigenvalue. Well, actually, these two guys is relevant to Willmore conjecture. And I will say it at the end of this talk. Yeah, my conjecture, okay. Okay, so based on this, okay, so sounds like right now we just asked the first question, which function is suitable for the fourth order Willmore problem, right? And the next, we need to find the suitable class to consider the infima. And here, we can
So I have
change
another
our
question.
yeah
I'm lost. Where is your fourth order?
fourth order because
Yeah,
okay, let me say it in this way. Because
yeah.
under the dilation and the Rubin grams energy, I should say, so the volume here is a 4, okay? And the integrand, if I add a tilde, like this, and it will be 4. So the reason is here, because here is a 4. So we call it the fourth order Willmore energy.
Oh, I got it because you do rescaling. There is a fourth.
Yeah, because when we do the
Okay, that's a
rescaling, the
reason.
integrand, the dilation of the integrand is -4.
Yeah, now I get it.
Yeah. Okay, so okay, let's continue. So before we continue, we need to revisit Leo Simon's criteria. So as I said before, right? So Simon's criteria can be regarded as to avoid the obstruction, okay, to the splitting. And right now, we can think it in the following way. So this criteria can show that how the conformal transformation will affect, I mean, the minimizer surface in this progress, right? Because in dimension 2, the topology is too simple. When we fix the genes, right, the topology is totally fixed. However, in dimension 4, the topology is too complicated. So we need to investigate how the conformal transformation will affect the topology. For this reason, we calculate the loss of the energy under the inversion. And we find that totally similar to dimension 2. Here, we assume 0 exactly the point on our hypersurface or submanifold, and we consider the inversion, okay, center this point. We find that we will lose the energy. Okay, this is the energy of the sphere and the times the number of the per image. Okay, and the next, of course, if you would like to prove this identity, you can, do the direct calculation. However, you will see that if you do the direct calculation, use the Rubin grams energy, it will become very complicated because you don't know how to calculate the residue at this, pull-up point. And to simplify our calculation, I will use the formulation in terms of the extrinsic Pendas operator and extrinsic Q4 curvature. So this is the work as I introduced. So based on my advisor's result, they define, okay, a family of extrinsic GGMS operator. And in dimension 4, okay, it's given in this form. And you will see that the leading term exactly the bilabas, okay, and you have some lower term. And here's the tensor. Since in this critical dimension, we do not have the constant term. And the constant term exactly extrinsic, okay, Q curvature. And when we take the integral, so the total, okay, Q curvature exactly 2 times Rubin grams energy. So you can see that we can consider, let me write down here, if you consider the inversion, so compose with the inversion, and you will see that the conformal factor of this new metric under the inversion is given by this conformal factor. So you can plug into this transformation law. Since we have the bilaplus, right? So you can apply the integration by parts to calculate the residue. So based on the similarity of these two entities, we investigate the geometric interpretation. Okay, so the interpretation is the following. So we already have the extrinsic Q curvature, right? And right now, we consider the intrinsic Q curvature. The reason is the following. Because when we consider the intrinsic Q curvature, we can link the total Q curvature to the Gauss-Bonnet formula. So let's briefly review the intrinsic Q curvature. Here is the formula. Okay, it's given by Laplace scalar curvature, squared scalar curvature, and this part. Okay, and totally similar. We have the Penna's operator. The leading term of the Penna's operator exactly, by Laplace. However, the lower term, okay, is totally different from extrinsic Penna's operator. However, if we consider the difference, such that we can cancel the leading term, and we only have, okay, this lower term. And based on our calculation, and we will find that if you plug this conformal factor, okay, into this lower term, this guy will not, okay, provide the loss of energy under the inversion. So it sounds like if you take the integral, the difference of total extrinsic and intrinsic Q curvature consists of 3 parts. These two guys, they are pointwise conformal invariants, okay? So under the inversion, these two guys, okay, they will not change. And this guy is something new. So the integrand in the bracket is not pointwise conformal invariant. However, this part, okay, is invariant under inversions. So it sounds like this guy will not provide the loss of energy under the inversion. So for this reason, you will see that the loss of energy is totally provided by the change of characteristic. Since by Gauss-Bonnet train formula, we can, reformulate the total intrinsic Q curvature by characteristic and minus the Weil tensor. So this is a Weil tensor. But no worries, this guy is invariant under inversions. So for this reason, we can say that Rubin-Grimes energy, the leading part is exactly the characteristic and their difference and the Weil tensor. And the last two terms, okay, they are invariant under inversions. So right now, we only need to investigate the change of the characteristic under the inversion. And by the basic knowledge, okay, by Huijing theorem, we can say that under the inversion, the characteristic will be changed by this formula. So sounds like we need to minus, okay, the number of pre-images. Moreover, on a complete but non-compact, okay, four-dimensional submanifolds, the Gauss-Bonnet train formula will be changed because right now we need to minus the idoparametric ratio of each end. So to the best of my knowledge, the study of this topic started from, let me write down here, Alice Chang and Qing Jie and Polo Yang's work. Okay. However, in that case, they consider the intrinsic vision such that they need several positive scalar curvature conditions to rule out some pull-up terms in the asymptotic expansion. So the reason is the following. Because if you consider biharmonic equation on the pinched Euclidean space, and you will see that, here's the P4, okay? And you will see that there are 4 solutions, 4 radial solutions, constant, R square, R minus 2, and log term, okay? However, for these 4 terms, not all of them is well-defined, not all of them has well-defined isoperimetric at infinity. So you must need the positive scalar curvature, this condition, to rule out some of them. However, in our case, we are very lucky because we use the inversion rate to, block this point. So all of ants in our setting is asymptotically flat, such that the parametric ratio is constant there. Sorry, is constant 1. Okay, so we need to minus. Let me emphasize. We need to minus 2m here. So 1 over m from here, another m from the parametric ratio, and for this reason, we need to minus energy of the sphere times the number of the pre-image. So it sounds like in fourth order Willmore energy, the change of the topology is totally determined by characteristic. So for this reason, we formulate this problem in the following way. Again, we consider a suitable Willmore energy, but right now, we do not consider all of the emergence from closed 4-dimensional submanifolds with fixed topology. Instead, we consider emergence from submanifolds with the same characteristic. And we highly conjecture that in this minimizing process, we can preserve characteristic, but we cannot preserve the topology. And we are working on the existence, but we haven't finished it because it's a little complicated. Okay. And totally similar to Banner and Kuwert's result, we can obtain the following estimate. Of course, this estimate can be used to avoid the splitting as long as we can establish the existence. Okay, but here, since we are consider fourth order Willmore energy, right? So in the neck region, we need tree harmonic interpretation. Okay. Okay, so next, I will briefly introduce the energy quantization. A work we are working on. So first of all, let's briefly review the energy quantization in dimension 2. Here it's based on Yuxiang Li and in-house work. So in their setting, we can consider a sequence of conformal and Willmore emergence. And there are 4 assumptions. So the first assumption says that the cylinder, will become a long cylinder. Next, the second assumption says that if you consider, the unit interval, but you can translate it to infinite, the energy, concentrated in this unit interval converges to 0. Here, it says that no bubble. So it means there is no concentration of the energy, And the next, so next assumption says that we can assume, our immersion is conformal. However, for this conformal factor, we need additional assumption. The reason is the following. Because in their proof, we will do the block analysis. So finally, we will find a surface on pinched, R2, and the signal fundamental form is 0. However, because in dimension 2, we do not have the Liouville theorem. So right now, we cannot claim that the conformal factor is constant or a function of t, because let me write down here. Because the flatness can only say that the conformal factor is a harmonic function in this pinched space. So we must add this uniform gradient estimate to rule out other harmonic functions, such that in the blob, so if we have this assumption, it will imply that u exactly this function, m times t, and m exactly an integer, such that the blob metric is given by this guy. Okay, we have some winding, okay. And the next, so the last assumption says that all of these immersions can be regarded as part of the immersion defined on a closed surface. And the benefits of this assumption is the following. We have conservative loss. So under assumption 4. Because as I said before, right, Willmore energy is conformal invariant under translation, is invariant under translation, dilation, and rotation like this. So if we have assumption 4, we can calculate the force variation such that we have some conservative loss. Okay. And the main problem is to show that in the neck region, okay, the neck region will not, take energy. And the positive answer of this question follows from the following claim. And this is that as long as the L2 norm of the second fundamental form satisfies such kind of exponential decay, and we are done. And if you are very familiar with harmonic map, you will see that this exponential decay follows from 3 circles lemma. So in Yuxiang Li and Haoyin's work, this is that, so here the assumption, we have a sequence of conformal Willmore inversions, okay? If you have 2 conservative laws, so this guy from translation, the second guy from rotations. So we have 2 conservative laws. We have the uniform gradient bound, and we do not have the concentration of energy such that we have the exponential decay. And here are several key points. So as I said before, the key term in the proof is 3 circles lemma. First of all, let me say it in the following way. First of all, we need to choose a function. And next, we do the blob. And to guarantee the start of the blob, we need the epsilon regularity. Epsilon regularity says that in the interior part, for example, t plus epsilon, t plus 1 minus epsilon, okay. In the interior part, we can always choose a constant such that it will be bounded by the L2 norm of the total energy or the average mean curve, whatever, such that we can start the blob analysis. And the equation under the blob exactly harmonic equation, right? Because only the leading term will be left. So it sounds like we need to establish the 3 circles lemma for harmonic functions. However, even for standard harmonic functions, 3 circles lemma is not valid because we have two obstruction terms. Okay, from my point of view, the obstruction term in 3 circles lemma is exactly the constant term. The reason is the following: because if it's a constant, right, when you take the integral on a fixed length tube, okay, it's constant. So you do not have the exponential decay. And right now, because the metric under the blob is this guy, okay, so you can see that for this exponential mt cosine exponential mt sine, their L2 norm exactly given by the following. And here you need to multiply exponential minus 2mt. And you can find that exponential term will be cancelled. And for the cosine term, okay, the integral is constant on a fixed length tube. Okay, so it sounds like we need to rule out these two abstraction terms. And here we need, okay, let me here we need the conservative loss. Okay, so these two guys will vanish. And finally we are done, because as long as we can establish the exponential decay of the L2 norm of the mean curvature, we can compare it with the L2 norm of the second fundamental form. Okay, and you can find more details in their work. Okay, so right now, if you would like to do the same thing for fourth order Willmore energy, first of all, we need to clarify the Euler-Lagrange equation, right? So the Euler-Lagrange equation for the Rubin-Grimes energy is very complicated. So here I list the first variation of 3 building blocks in this functional. And you can find that the leading term exactly the biharmonic term. Okay, so as you can image right now, if we can do the block analysis, the equation under the block exactly the biharmonic equation, such that we need to establish this 3 circles lemma for this biharmonic equation. And right now, we already established the epsilon regularity. So this epsilon regularity says that if we consider the image, okay, of this smooth Willmore hypersurface, for example, if you have a point here, and we can find a extrinsic bore, okay, so this bore is extrinsic, and such that we can use as long as the total energy, okay, is very small in this extrinsic bore, we can establish the interior estimate, such that if you have a tube like this, and we can use the covering argument to obtain the, global interior estimate. Of course, as long as we can obtain this, we can use the Euler-Lagrange equation to control all of high order derivatives. So next, so you can see that in previous result, right? This smooth Willmore, hypersurface is fixed. But if you consider a sequence of Willmore emergence, you need to deal with the following question. Because in our setting, right, the bore here is exactly the extrinsic bore. So if you have a sequence of emergence, right, we do not expect this bore, will be collapsed. So in other words, if you have a sequence of emergence from a fixed surface, and if you choose a intrinsic bore here, you have an intrinsic bore, and we would like to compare the size of this intrinsic bore and this extrinsic bore, such that you can see that for this sequence of emergence, we can apply the previous theorem, right? And for this purpose, we need to estimate the conformal factor, okay? And we can obtain the uniform gradient estimate for the conformal factor, such that for this fixed intrinsic bore, their image will not change a lot. Okay. So this is our setting. So our setting says that for this fixed surface, okay, sorry, for this fixed hypersurface, we can consider a family of emergence, okay, and composed with emerging here, we can consider a family of pullback matrix. And here, we assume, okay, this sequence of, pullback matrix, they have convergent conformal class. So what does it mean? It means in their conformal class, we can find G tilde I, and G tilde I will converge to this fixed metric. Okay, so there is no collapse, okay, of their conformal class. So this assumption is totally equivalent to the convergence of complex structure in dimension 2. Okay. And further, we will, three circles lemma is almost done. And I think the preprint will appear this month or next month. And before, at the beginning, we spent some time to consider the existence of the minimizer, okay? However, it's very complicated. Since I do not have enough time, so I do not want to say more about it. So finally, let me spend 5 minutes to briefly introduce the fourth order Willmore conjecture. So Willmore conjecture says that if we consider a minimal surface in S3, let me say it in the following way. So if you consider Willmore surface in S3 and genes bigger than or equal to 1, such that the minimizer is obtained by cleft torus. Okay, and the key point in Marquis and Nevi's proof is the following result. Let me see, Urbano's result. Urbano says that if you consider minimal surface in S3, such that index of this guy is at least 5, and the equality holds if and only if it's cleft torus. So here, the number 5 follows from the following observation, because we can consider S3 as a unit sphere in R4, right? And in R4, it can provide 4 coordinate functions. Because these 4 coordinate functions, there are non-trivial conformal vector fields on S3. And another direction is given by the spherical distance function. So it says that along these 5 directions, okay, the the volume of this minimal surface will decrease, okay? And right now, if you consider Rubin-Grimes energy, and for convenience, we modify it. So as I said before, we have this lower bound, right? And we have the volume function. So of course, we would like to establish some characterization of higher order cleft torus. What I mean is, if you consider S2 times S2, and you can, you can do the calculation by yourself. And here I will just give the answer. I denote this functional is F1, and this guy, I denote it is F1. This guy is F2, and this guy is F3. And you will see that S2 times S2 is a local minimizer of F1 and F2. So you can find that this guy is totally different from 2-dimensional case. Because in 2-dimensional case, this guy is the analog of conformal area. So cleft torus is exactly a saddle point. However, in 4 dimension, it's no longer a saddle. It's a local minimizer, but it's not global minimizer. Moreover, here we do not have index, right? The kernel, dimension of the kernel is 7, because S5 is a unit sphere in R6. So you have 6 coordinates function, but right now they are in kernel, and you have 1 provided by distance function. So dimension of the kernel is 7. However, this guy is a saddle, of the volume function, and the index is 7. So it sounds like right now we need to use functional F2 and functional F3 together, okay, to characterize S2 times S2. However, here is one more observation. If you consider S1 times S3, and you will find that this guy, okay, is no longer a functional of F1. However, this guy is no longer a critical point of F1. However, this guy exactly a critical point of F2 and F3. And the dimension of the kernel is exactly 7. So in other words, if you directly consider, if you directly use F2, F3 dimension of the kernel, I don't think you can distinguish S2 times S2 and S1 times S3. So in the formulation, I highly conjecture that we need to add one more direction. We need to fix the characteristic, because characteristic of this guy is equal to 4, and the characteristic of this guy is equal to 0. So it sounds like the formulation should be the following. If the characteristic is 4, dimension of the kernel is 7, and the index is 7. Of course, this is F2, okay, and this is F1. And can we say that this guy is exactly S2 times S2? Okay, I think I should stop here. Thanks for the attention.
Okay, so is there any question? Okay, no questions. Okay, so there's no question, Zetian. Okay.
Yeah. Okay.
Take a shower, go home.
Okay.
Okay, thank you for your nice talk.
Okay, thank you.
Yeah.
Stop sharing.